Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Izzaudin bin Ahmad from Group 3. So today I will explain the objective for experiment 3, which is shearing force in a beam. There are three objectives for this experiment. Firstly, comprehend the action of shear in a beam and measure the shearing force at a normal section of a loaded beam, and to check its agreement with theory. Next, conduct the experiment correctly and identify the dependent variable and independent variables, record, tabulate, and analyze raw data, and also measure the shear force variations. Lastly, demonstrate work effectively and cooperate in a group to complete the laboratory tasks. So that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. I am Muhammad Bayab dengan BSV. I come from Group 3, Section 2. Today I will present about experiment shear force in a beam. So, in this experiment, the equipment that we use is a weight hanger that present 10 gram and a load present 10 gram. And the last one is steel ruler. Third is we need to check that the wire is connected to input 1 and the display adjust to input 1. And then we set to 0. Set to 0, we need it just at here. So it's done. It is set to 0. Then we replace the weight hanger. So based on lab sheet figure 3.5, we can know the placement of weight hanger is 40 mm from the cut. So we measure the 40 mm. Okay, we can know the 40 mm from the cut is at here. So we just place the weight hanger at here. So we place the 100 gram load and press. Therefore, we can know the shear force is 0.6 Newton. And then we repeat the procedure that increase the mass to 200 gram, 300 gram, and 400 gram, and the last one is 500 gram. That's all. For the experiment 2, is shear force variation for various loading conditions. This experiment is to examine how shear force varies at the cut position of the beam for various loading conditions. From this lab sheet, we have the figure force diagram 3.6, 3.7, 3.8, and from this we can know the placement of weight and the value of gram we need to place. So for the figure 6 is we need to measure 140 mm from here, and it's come from here. So measure the 100. Di sini. Okay, 140. Okay, you can see here to here is 140. Therefore, we place the hanger at here, and we need to calculate the RA and RB. So we place the 3.9 Newton or 400 gram at here. So this is 400 gram, that equal to 3.92 Newton. So we place place this 400 gram at the place that we measured before this, at here. And the display force is equal to 0.29 Newton negative. So we put the data into the table for the figure 3.6 force diagram. And the next force diagram is 3.7. It use 200 gram for the weight one and 400 gram. For the weight one is 220 away from here. Here to the left is 220 millimeter, and for the weight two is for 260 millimeter away from way right to this, from this to here. Measure 220 and from the sini 220 and 260. Mana? So 222 millimeter is for 200 gram. Come here. So we put this, and then for 400 gram at 260 millimeter, therefore is here, at here. And the shear force is equal to display force, that is 0.8 Newton. And next, result from figure 3.7 force diagram. And next we going to figure 3.8 force diagram. For the weight one is 4.91 Newton is equal to 500 gram, and the weight two is 3.92 is equal to 400 gram. So we take back the weight for this 400 gram and this 500 gram. This is for weight 1 and this for weight 2. So we measure the 240 from here to the right, and 400 millimeter from here to the right. So for the weight 1 is 500 gram. That's placed to 240 millimeter at here. Lagi. And for the weight 2 is 400 gram. For 400 millimeter from that is here. You can see 400 meter. Okay. So the force is 0.5 Newton. That's all. Remember, the shear force at the cut is equal to the algebraic sum of the force acting to the left or the right of the cut.
Assalamualaikum warahmatullahi wabarakatuh and very good morning. So my name is Muhammad Ismail. So for the discussion, I'm going to analyze and differentiate through a brief discussion based on data obtained from the network. From the shearing force in the beam network, we have conducted two sets of experiments. In the experiment 1, there is a shear force variation as a different load is administered when there is no mass introduced to the beam. The resultant shear force is 0 Newton, where there is mass of 100 gram. The shear force is now increased to 0.6 Newton as the mass keep increasing from 200 gram, 300 gram, and 400 gram until 500 gram. The resultant shear force keep increasing to 1.2 Newton, 1.7 Newton, 2.3 Newton until 2.9 Newton relatively. Hence, we can make a conclusion the shear force is increasing with the shear increasing of the mass. In experiment 2, the experiment is about to shear force for various loading conditions. From the data sheet, there is only a small difference between the values of experimental shear force and theoretical shear force. For the figure 7 and figure 8, the value of the experimental shear force is 3.1 Newton and 2.3 Newton, which is almost the same compared to the theoretical shear force of 3.3 Newton and 2.32 Newton. As the figure 6, there was a small difference. The experimental was 1.3 Newton and theoretical was negative 1.25 Newton. So comparing the shape of the graph, what does it tell us about how shear force varies due to increased load? The sketch graph for experiment 1 is a linear graph, but of the graph passed through an origin, which is 0, 0. This means shear force is not existing when there is a no load. From the graph, we know the shear force is increasing when the load is increasing. This conclude the shear force is proportional to the load applied on the beam. The slight difference between the experimental and the theoretical value of the shear force is probably due to inaccuracy when conducting the experiment. In experiment 2, the photograph show the margin of error between experimental and theoretical shear force is very small. This also may happen due to measurement error and sensitivity when conducting the experiment. So comment on how the result of the experimental compare with the loss calculated using theoretical. So the experimental result and calculated theoretical result again are slightly different. The experimental result are lower than the theoretical result. This is probably caused by inaccuracy measurement error, sensitivity of the beam, calibration inaccuracy, or the load angle is moving or shaking. That's the equation we use accurately predict the behavior of the beam. So the answer is yes. The equation S equal to SC equal to W dot A over I that was used in the experiment for theoretical shear force for calculation accurately predict the behavior of the beam. Also, in the bending theory, when a force within a point gets passed through the longitude axis of the beam, bending theory refers to the cause of axial deformations such as stresses. This can also show from a bending equation, which is sigma over y equal to E over R or equal to M over T. Next question, what are possible things that cause there to be a percentage error between the experimental and theoretical value of the experiment? So based on the research, the possible thing that can set the percentage error between both values are such as the lighting is shaking, the beam is sensitive, the jitter indicator is roughly accurate at low values we measure, the jitter indicator is too sensitive, and lastly the calibration inaccuracy. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Nadrai bin Zahari. My number matrix CN200046. I will talk about the conclusion for this experiment. From this experiment, we were able to determine that when the beam's modulus of elasticity is higher, the beam becomes stiffer. An internal force is created by the applied load, which consists of shear force and bending moment. The data demonstrate that when the overall mass grows, the load, experimental shear force, and theoretical shear force all increase. It can be stated from this lab experiment that as the weight applied to the beam increase, so does the shear force. It was also established that the shear force at the cut area is equal to the force operating on the beam from both the right and left side of the cut section. That's all from me. Thank you.